So we're on our second day of rotational spectroscopy, and what I thought was kind of curious was just starting out, we have this rotational constant B, h bar over 4 pi ci. Now, Pablo, you remember what I was?
Inertia?
Yeah, that moment of inertia. Yeah, because when you have objects that are spinning, right, like A and B, and you want to characterize their motion, what mass do you plug in? Do you plug in their sum of their mass? What mass do you plug in? Do you remember this? And
It's a big one?
yeah, like you have this object AB, right? And just like a diatomic molecule spinning, right? How do you characterize its mass? We have to combine them, but it's not sum, it's not total, it's right? Someone's remembering. What do we call it? Surf and R. Yeah, I think that's also a symbol for dipole. Reduced mass. We call it reduced mass. So in this book, oh, what was it? We might as well just finish the story. It was you multiply them, pretty much what Brad was saying, divided by it's in the concept review stuff, probably a ways back, but that's what it was. Okay, so you're probably wondering, why the heck is Smith even talking about this? Because it doesn't even show up over here in this equation, does it? Or does it? What's I? What's I?
The sum of the moments of inertia?
I is the moment of inertia. I is the moment of inertia. So depending on the molecule that you have, so I've been holding this thing for a while, page 464, are all these different molecules, right? And they give you the expression to calculate the moment of inertia. And it's kind of curious, though, out of all these molecules, we're only going to be using one of them. Hesitate to guess here? Diatomics. We're not going to think of anything more complicated than that. Diatomics is complicated enough. So we're only going to be using that equation number 1, right? So the moment of inertia is the reduced mass times r squared. So r would be what?
Radius between the two?
Yeah, but between the two. But you would call that what? The bond length, the bond length, the bond distance, right? So that's just wanted to bring that stuff out. I mean, it kind of looks ugly, this whole thing, but you really don't need to worry about it. Only equation 1. Okay. Now they want, I think it helps to remember what stuff units are in. They really like wave numbers for this stuff. So let's just help them out by identifying all this. Okay. So now they're getting into rotational terms. So you can describe a state, a rotational state. And it looks, so f of j describes a rotational state. So what are they using that looks like, Brad, is their quantum number to describe the, I need quantum numbers to describe states, and we luckily skip all the math and deriving all these things, but what is their quantum number to describe a state? The J. The J is their quantum number, right? The J is their quantum number. So what I think is interesting, though, is look at their state. To describe a state, it's B times J plus 1. Now, J is just a quantum number, right? 1, 2, 3, 4, 5, 6, 7, just a whole number. So that means this f of J has to have what units?
Meters.
Does J have any units? No. So rotational terms that they are referring to describe the different states of rotational energy levels have to have units of the same as what? As B. What's B? What do we say units of B are?
Wave number.
All right. So the reason why I bring this out is I think I'm used to, oh, what's this rotational state? Aren't you expecting to put joules on it, right, to describe a state? They're describing these states as, just have units of wave numbers. But you can you calculate energy? Can you calculate joules if I give you a wave number? Ricky, can you calculate joules if I give you a wave number?
I don't think so, but I don't know. Wave number, that's gonna be lambda. So can I calculate joules? Yes.
Yeah.
Just E equals the HC over Q.
You bet.
Called?
Yeah, I can give you give you a wavelength. You know what the energy is. I could give you a frequency. You know what the energy is. I could give you a wave number. You know what the energy is, right? So we have expressions for all that, and go back and you can review those. But what the book is going to be talking a lot here is I want you to do this. Let's call it HWK1, homework 1. Okay. I want you to show that f of j minus f of j minus 1 equals, and I'll fill in the blank. But we're going to do the math to do that. I mean, that's what the homework will be. But what are we finding here? Right, if this is state j, this is state j minus 1, we're finding what are we finding? Think of these as energies, because they really are. Ricky said you could calculate energies out of them. Energy of the j state, energy of the j minus 1 state.
Is it the energy between states?
Energy between states. Now, why is that a big deal? Why is that a cool thing to calculate? Because this is all about
Phosphorescence.
it's all about what? Spectroscopy, which is what? Light and matter, interaction between light and matter. So I think getting the difference between two energy states is key. That's spectroscopy. Okay, so I want you to find what f of j minus f of j minus 1 is. All you do for f of j, plug in bj times j plus 1, right? F of j minus 1, plug in b times j minus 1 times wherever there's a j, you have to put in j minus 1. So you'd have bj times j plus 1 minus the same expression again, but wherever you see a j, put in j minus 1. And see what it is. Okay? So you need to show that it's 2bj. If I remember right, yeah, 2bj. So you plug in those two and you show that. So if that's the case, I'm sure the homework's going to hit on this a lot. And they say they'll give you the states, right? And they probably want wave numbers or frequencies or whatever. This is the energy between the states. Just remember, it's in the wrong units, in inverse centimeters. But what j do you use? They're talking about j going from, I'm just making something up. Let's say they're talking about j going from 3 to 4. The homework question deals with it. It could be anything. They want you to calculate the bond length, and they want you to calculate the frequency, the wave number, whatever the question is. Which j do you use if you want to use that expression? Would you use the 3 or would you use the 4?
And we're calculating what? The difference between the states?
Oh, just pretend. Make up your own homework question. But the homework question entails you using this expression. Which J do you use?
I would agree with Brad and say it's 4.
So look at how you derived it. F of j minus f of j minus 1. Would j be 4 or j be 3 make more sense? If j is 4. Because you'd have f of 4 minus f of 4 minus 1, which is 3, and that's what you're finding. You want to find f of 4 minus f3, right? That's what you want, the energy difference between those two states. So you're always going to plug in the which j? The biggest j. Okay. So since this is the separation of energy levels, right? Again, I just want to remind you, it's not in units of what, though? It's in units of wave numbers, right? Not joules. But so here's our separation energy levels. Is it consistent? I mean, is it constant? Is it a constant separation as you go up the energy ladder, right? Because the energy ladder says higher and higher J. Is it a constant separation? Or not? J going from 3 to 4, J going from 5 to 6, J going from 7 to 8. Is it a constant separation? That's what the picture's showing you, right? That separation keeps getting bigger and bigger and bigger. And that's what they're saying over here. Yeah, the separation between rotational energy levels just keeps getting bigger and bigger and bigger as J increases. Principal axis, we've talked about principal axis before. Exact same idea as in group theory. I wanted to show you some rotational modes and stuff, just to remind you of what we're talking about. So we're talking about this sort of thing, right? Like here's carbon dioxide. It's rotational modes, okay? Microwaves, right? How they work. Okay. Bet you there's one transition more than the other one in there that's hitting up microwaves. Okay. Oblate and prolate, that's a DWA. Don't worry about it. Okay. The Stark effect. These states only depend on what quantum number? J. But what the heck? I mean, do you remember? You have to go back and remember all this stuff. But if I give you a J, what goes from negative J all the way up to positive J? The M sub J's. Well, I don't see and where it says the state F of J, I don't see this J comma M sub J and describe the state. No, it doesn't show up. So that means that each J state is what? The D word. D degenerate, right? In order for you to see all the M sub J's, you have to turn on an electric field. You turn on an electric field, and bam, you see all the M sub J's, all the degenerate states. Okay. So there's some talk about how I guess I really don't like it when they try to conceptualize these things, because somewhere they're wrong, because quantum mechanics doesn't describe baseballs flying through a field. But they're saying that the electric field, it actually kind of pushes things around. It's going to push some things closer to the nucleus and make them lower in energy, and some things farther away from the nucleus higher in energy, because that's the electric field. That's how it interacts with those outer electrons, and I don't know. But So if that helps you, I don't know if it does or not. But so anyway, the point is Stark effect will show you that all those little m sub j's. Otherwise, you don't see them. Okay. Centrifugal distortion constant. So I added this because I don't think it was in your notes. I added it this morning. Only worry about the concept. Only the concept here is really important. But what is the concept? What's going on? What's going on? Has a lot to do with this page 464, even though we're only going to use one equation on it. If you were, let's see, if you were that little, especially this one. Think of it as one of those rides at Fiesta, Texas, right? That's Ashley and Mike swinging around, right? And that ride I hate, it's the 8-ball. It makes you sicker than a dog. You feel the whole time, you feel like what? You're pushing away, right? If that seat wasn't there, wouldn't it distort? Would be the technical word for it. Their shape would distort. So that's called centrifugal distortion. Centrifugal distortion. Is that a force? For once, they don't call it force. That's why I like these P chemists. They got their act together because they're really big on physics, right? You have that object spinning. There's only one force. There's the C. Centripetal. And it's directed where? Towards the center. Only one demonstration I have to prove it.
Which makes no damn sense.
I know.
but I saw the flame do that. So
but the flame goes towards the inside. It makes a lot of sense if you think about if you put a ball on a string, right, and just swing it around like David and Goliath, right? If you snip that string, is the ball going to stay in the circle? No. So there's a tension in that string. The tension in that string is centripetal force, right? Why does the ball go flying off when you snip the string? That's just the I word. Why do objects want to keep going in a straight, perfect line until acted upon by an unbalanced force? Inertia. That's inertia. Okay, so they're saying that this cannot happen if you want to use page 464. Because these are what rotors? Rigid. They distort under rotation? They better not. Otherwise, forget it. Right? Okay. We're not worried about centripetal force. We are worried about centrifugal distortion. Because we want to calculate a lot of your homework. You're going to spend the next 5 or 6 hours calculating the bond length of HCl or something. The homework just keeps asking for this. All of these bond lengths. Fine. So, and I just know that I don't know how else you would get it without using this equation, okay? Because there's R in there. I is mu R squared. So if your HCl or whatever is distorting under rotation, you're not going to calculate the right bond length. Okay. Rotational transitions. It's our selection rule. Okay. So we have our allowed J to J plus 1 transitions. Okay. I'm just getting this from the book here. Okay. So what J are you going to plug in here? You're going from J equals 5 to J equals 6 rotational state. Which J would you plug in to calculate the wave number for that transition?
6.
6, right? Oh, hold it. Sorry. This is set up for J going to J plus 1.
Oh, so we're using a
So you have to use, if you're going from J equals 5 to J equals 6, look at the expression. They're allowing you to skip all the math. You just have to use it. You're going from J to J plus 1. So to make this work, J has to be 5 or 6. 5. Because you're going from 5 to 5 plus 1. So to plug into this expression, you got to plug in the lower one. Okay? Yeah, they did. Okay.
So the last one was for what? Like getting excited, and this one's for not.
This is an allowed transition. The other one is for describing, they were talking about differences in energy levels. So it seems to me they're pretty darn, just made 2 different ways of calculating the same thing. Yeah, there's 2 different ways of calculating the exact same thing, because look, they're changed by a 1. Isn't that crazy? Right? How many of these do you need? You only need 1 of them, because this is J plus 1. Well, I know, that's just what the book's doing. But I'm glad you noticed that. Now this is for, if you talk about linear molecules, some more selection rules would be like delta J has to be plus or minus 1. Delta M sub J needs to be 0 or plus or minus 1. Then they have something called a pure rotational spectrum. And this is what I was trying to look up. If you have something that is a permanent dipole moment, you get this really beautiful structure. I mean, it looks like a butterfly kind of with the wings, but it has to have a permanent dipole moment. Now, if it's going to have a permanent dipole moment, who's the C's, right? I'm thinking of group theory. If you want something to be permanently polar, it needs to be a member of the C group. Remember that? C, N, C, N, V. Yeah, C, S. Yeah, the C stuff. Okay. Okay.
I don't know. All I know is that we probably did not.
Oh, and I forgot his little award. I'll have to get it. No, that's not okay.
It's not okay.
Rotational Raman Spectra. We'll get the exams back at the end of the hour here. So if we're talking about Raman now, do you remember what was the, for example, if we go back and say Ftir, what did the molecule have to exhibit? Had to have vibrational with an oscillating dipole. Okay. What was the case for Raman? Well, Raman, you can gain energy or you can lose energy in the scattering process. But what had to happen for that light to interact with matter and call it Raman spectroscopy? With Ftir, it was an oscillating dipole. With Raman, it's, Ashley's supposed to name her child this?
Oh, that weird name.
Yes.
We did it on Friday.
And he has no clue. And isotropic half of it. Polarizability.
That's what she's supposed to name her child?
It was just a joke. Jeez.
I like Bradley
Okay.
Bird better.
Now, go back to Ftir. Was there a molecule? Can you name me a molecule that will not exhibit Ftir? You can't see it. It's invisible on that Ftir. Yeah, give me a molecule that you cannot see. Something that will not exhibit an oscillating dipole. Say it.
Hydrogen gas.
Nitrogen gas, homonuclear diatomic gas, right? There's a lot of things like that. And there's some vibrations. Like look at benzene. We had some vibrations. If you don't see an oscillating dipole, you're not going to see that vibration happen. It'll be invisible. Okay? With the FID detector, what's a gas that's invisible?
Oxygen.
Yeah, because FID detector on the GC is a what counter? Carbon counter, right? So a lot of these systems, there's a good range of things they can't see. Now Raman, man, it's very, very narrow what it cannot see, because pretty much everything exhibits anisotropic polarizability. So much so that it's a lot easier to memorize the dudes who don't. And the dudes who don't are on the very bottom of page 464. Called the what rotors? Spherical. The spherical rotors are the only ones where you can't see. They're invisible. Raman spectroscopy can't see them. Give you an example of one. A perfect tetrahedron would be carbon tetrachloride. So this is what you're going to kind of see when we're talking about pure rotational spectra. You're going to see something kind of like that, but not really quite, but it'll be pretty close. Since we're talking about this rotation, all this is about rotational Raman spectroscopy now. The separation and I'm giving you this because it must be in the homework, otherwise why else would I have written it down? Between adjacent energy levels. Now again, this is for what type of interaction? Raman. It's for Raman spectroscopy. The separation between energy levels is 4b. Okay. So, and here's your energy levels. Just take this plot, rotate it 90 degrees. And look at that. You even see their populations on there. Okay. You rotate it 90 degrees. You have your Stokes and your anti-Stokes. Higher gained energy, lost energy. Okay. So the book also wants to hit on, since all we're talking about are linear rotors here, we have our selection rule for Raman. I should do like this. And that's where delta J is plus or minus 2. Right? And what was a big expression? There it is. Wave number J going to J plus 2 was tilde with an I minus 2b, what is that? 2J plus 3. So let's make sure that I is clear. What is this little I doing in here? What's so special about Raman? Do you remember Raman spectroscopy? What they're interested in is you have your molecule, right? In this case, it's rotating, and it exhibits anisotropic polarizability, so it can, when it scatters radiation, right? It'll either increase the frequency of the scattered radiation or decrease the frequency of the scattered radiation. That's the whole idea with Raman, right? So you're not looking at the molecule, you're looking at the scattered light, aren't you? That's all you're interested in Raman is the scattered radiation. So this little I probably stands for what? What do we call little I?
Conditional.
initial, but they like another word better. It's close. That's the right idea, but in
Oh, intended?
incident, incident, right? I like the word. I don't know if it stands for incident, but I like it standing for incident because it might be initial, but I think incident is a much better concept because it's incoming, right? Or I guess that'd be another I word. But incident is nice because it just helps me visualize, oh man, it's going to slam into it, right? It's incident. So it's before anything happens. So that's the incident wave number of that incoming radiation. Okay. Nuclear statistics and rotational states. I don't know. There's a lot of reading there. I would just say that that's the reason why we have that delta J being plus or minus 2, right? And only, and again in the reading, only even J's rotational states exist. It just all pretty much comes down to the Pauli exclusion principle. But I wouldn't worry about it too much. Okay. And this ortho and parahydrogen stuff, to me that's another DWA. Don't worry about it. Okay. So let's take a look at some of this homework. So we'll start with number 3. If the wave number of the J equals 2 to 3 rotational transition of HCl is considered as a rigid rotor, 63.56 wave number. So that's the wave number of the transition. What is the moment of inertia of the molecule? Okay. So since we have some equations and variables in them, what variable are we solving for here? That capital I. That's exactly where it starts, right? That capital I. Now, we have page 464 has a lot of stuff on it, right? There's all of our I's. You see the equation for it? I is, yeah, the very top one. I is mu r squared, or, right, the product over their sum of the masses times r squared. So, and we know we can use the inside front cover of the book to find the mass of those isotopes, right? We can calculate reduced mass, product over their sum. But I guess we don't know what the R is. What's the R? Bond length. So that's part B. So I guess we're not going to be using this equation to get I. We'll probably use this equation to get part B, though, right? I bet you we'll be using this equation to get part B. So how are we going to get part A, then? They give us the wave number. They gave us the wave number. I got to go back in the notes. That wave number has to equal what? So wave number of rotational transition. So we know the energy difference between states.
Do we have to use the rotational term to Fj minus 92 BJs and then solve for B with the Planck's constant pi?
You said it really fast, but you sound on the right track, right? So this is, no. What is this energy difference equal to? It was a homework that I called that HWK1 or something that you have to show. This difference, this energy difference between states, I know it's in the wave numbers, but it's an energy difference. You can calculate joules if you wanted. This energy difference is equal to what? 2BJ. That's equal to 2BJ. And what are you going to plug in for J? 3. Okay. And then Brad was talking about what B was. There's the expression for it.
Your rotational constant.
The very first one, right in the corner. Yeah, h bar over 4 pi c I. I don't know what you're talking about there. Right?
Solve for the I.
Oh, I forgot my 3.
Yeah.
And then we'll solve for the I. Now to make this work, watch your units here. I think the trick to doing this is have C in what units? C is what?
Meters per second. Meters over second.
Yeah, it's meters over second, but it's the speed of light. So yeah, in standard metric system, we have meters per second. But since over here we have wave numbers, what should we put this in?
Centimeters.
Put it in centimeters per second. Leave h bar alone, right? I think that would make it work. Or just, I would just put in your units for everything, and you'll see whether it's going to work out or not. All right? That's 3. 2 times B times J.
For the problem that you did, I think is that you use this transition from 2 to 3.
Let's say quick reverse.
Go back. So you do that homework 1 where you derive this 2BJ. That might help you realize why the J has to be the higher one.
Oh, no, I was just asking about the Ftir.
I left h bar units alone. But yeah, you might want to just put all your units in and find it. So we solve for our I. And then, do you see how to do this now?
Yeah, because of the yellow code.
Right.
You have I in the yellow code. You use solve bars.
How do you get mu?
Yeah, you stated. Why don't you look it up?
Right? Where? Do you guys remember how to do this?
The view,
Yeah, that reduced mass. Remember how to do this?
yeah, you take 2 masses times each other and then divide.
Yeah, what 2 masses? What numbers would you be plugging in for those?
For this one, you'll take the mass of your hydrogen and the mass of your chlorine.
Yeah, where are you getting those numbers?
I assume from periodic.
It's the mass of what? Is it the mass of Avogadro's number of them? It's the mass of how many of these isotopes? Just one. So what do you use? It's over here. Inside front, rear front cover. Little u symbol. Let's finish this thought first. Little u symbol, right? So here's all your isotopes, right? So you have the mass in terms of u. So you calculate your reduced mass. Like you said, their product all over their sum. Right? And you're putting in u's for these, right? Find the right isotope, rear front cover. But now it's in terms of u. So you have to convert that to, what was it? Kilograms over u. What number was that? Concept preview. Concept preview. We figured out how to convert u to kilograms.
Yeah.
Right? So these numbers are all in terms of u. all in terms of U, then you got to convert U to kilograms. So look at the concept preview. It was like 10 to the negative something. It was really small. Okay, it had to be. You find the mass of one hydrogen chloride molecule. Okay. So if you use the periodic table, that's the weighted average of isotopes. Yeah, you can divide by Avogadro and get that, but that's a weighted average of isotopes. You're not going to get the right isotopic mass here. Okay.
Yes, we're on to the next slide.
Go flip it all the way over to the back, inside rear front cover. Right? Masses and natural abundances of selected nuclides. Given the spacing of lines in the microwave spectrum, constant. For this one, well, how's that different from the one we just did? Oh, it's constant, right? I think this is where I was flipping open to the book. And this question, where did I see this? I don't know where I saw it. But how does this differ from the one we just did? Do you see it?
Probably a similar problem.
It's really similar. It's just there was a... It doesn't give you a J. It says that it's constant, so that there's no centrifugal distortion at all, and there was a... It was in the reading. I don't see it. How did I handle it? I said, it's got to be on page 4. I'll just write down the page number. Maybe you can find it if you're interested. Page 466. When it's constant, right? So you pretty much just say that before we had the wave number was 2bj, right? And J just goes from 1, 2, 3, 4, 5, right? It just keeps going up and up and up. So if it's constant, your spacing is just going to be 2b, right? So there's no distortion. And you plug in 2b times 3 plus 2b times 4, right? Subtract the 2, you always end up getting 2b. So before, we said that our wave number, this is the only difference. Before we said the wave number was this, right? The space between energy levels was changing. It wasn't constant. It was getting bigger and bigger and bigger the bigger J was. But now they're saying, no centrifugal distortion, so the spacings that are constant. So this doesn't really, you can use it, right? And just plug it in. Plug in like the difference between 5 and 6. Plug it in and calculate it, you get the wave number will be 2b. Just pick 2 adjacent J's and subtract them to get the energy difference between the two states. You always get 2b. So this question is handled exactly the same. It's just at the beginning you got to figure this out and realize that it's constant spacing. So my wave number is 2b. And then you do the exact same thing you did before. Okay. So I'll be around all day today and tomorrow lab. So come by with some questions on the